Hello friends, today we will see the combustion engine and the types of combustion engine. So first of all, we will see what is meant by a combustion engine. Here, the combustion of the fuel is carried out is called as the combustion engine. So we can classify this combustion engine into two types. One is external combustion engine and another one is internal combustion engine. So what is mean by how we can classify this external combustion engine and internal combustion engine? So first of all we will see external combustion engine. The heat is produced outside the engine is called the external combustion engine. And the example of this external combustion engine is a very well known that it is a steam engine. And next it is a internal engine. So here the heat is generated inside the engine is called as the internal engine. So which are the examples of this internal engine? It is a gasoline lines, diesel engine and petrol engine. So we will see the one by one engine. First of all, we will see the steam engine. This engine consists of three main parts. One is steam chest, second one is cylinder, and the main shaft with a flywheel. The chest and the cylinder are connected by steam ports P1 and P2. Here, the cylinder has piston P that moves without friction. So, to understand this internal construction of this steam engine, this is the diagram of a steam engine. So, what I said earlier that this steam engine consists of a three main parts. One is the cylinder, another is the steam chest, and this is the main shaft connected with a flywheel. This cylinder and the steam chest are connected by steam ports P1 and P2. The cylinder has piston P that moves without friction. The piston and the sliding wall, this piston and sliding wall are connected to this main shaft eccentrically at diametrically opposite points such that they move in a opposite direction. They are moving in a opposite directions when the shaft rotates. The main rod and the piston rod are connected in a such a way that the linear motion of the piston rod is converted to circular motion of the shaft. Phi is the sliding wall. Then we will see the working of this steam engine. The working substance in this steam engine is a mixture of water and its saturated vapor. Once again I will repeat here, the working substance in steam engine is a mixture of water and its saturated vapor. The ideal steam engine will be operated along the Carnot reversible cycle ABCD as shown in this figure. Here, the steam at high pressure soup of water from the boiler enters the steam chest. Here, this high pressure of a steam of water from the boiler enter the steam chest. The steam enters the cylinder through these ports P1. The piston P is pushed down due to high pressure of steam. The steam inside the cylinder, due to it, the sliding valve V moves up. Both the ports P1 and P2 are closed. The steam inside the cylinder, adiabatically, it expands and moves the piston further in the downward direction. At this point, the point P1 is connected to this exhaust valve E, and port P2 is now open. When this port P2 is open, steam enters through it and the pushes the piston up, and sliding valve moves down. The dead steam in the cylinder is exhausted out to the atmosphere through this exhaust valve E. Both the ports P1 and P2 are closed, and again the steam in cylinder expands. The piston is pushed further to complete the stroke. Finally, port P2 is closed and port P1 opens again. This process is continuously repeated. Means this process will be continuously repeated. The stuffing boxes B1 and B2 and crossheads C1 and C2 help for the smooth movement of piston rod, sliding valve rod, and the rotation of this main shaft. When piston moves up and down, the shaft is rotated. During the rotation of the shaft, the force acts at right angles to the shaft twice. The flywheel connected to the shaft keeps the momentum and enables the shaft to rotate beyond the dead center of each half rotation. That is, the flywheel rotates the shaft motion smooth and jerk free. Now we will calculate the power and efficiency of steam engine. Let P is the average pressure of steam. Here it is a average pressure of steam in, we can measure it into nano per meter square. Here L is the length of stroke, A be the area of the cross section of the piston. So therefore the total force on the acted on the piston is, we can write the formula, total force acted on the piston is pressure into area. So here the distance moved by the piston in double acting steam engine is 2L. Therefore, we will calculate the total work done acting on the main shaft. We'll write here the work done for one rotation of the shaft is equal to 2L into pressure into area. Here, if we consider that if a shaft rotates n times per second, then the work done per second is PA into 2L multiplied by n watts. So power of the engine is, if we know that all these three terms, then we calculate the power of the engine is equal to 2 into plan divided by 1000 kilowatt. Then we will see the efficiency of engine. The efficiency of Carnot cycle is given by, I can write here, efficiency of Carnot cycle is given by efficiency is equal to 1 minus T2 upon T1, where T1 and T2 are the temperatures of the source and to the sink. In case of heat engine, most of the heat energy is wasted in boiler. Therefore, the efficiency of steam engine is low and it is less than 10%. So the efficiency of this steam engine is very less. Then we will see the Rankine cycle. Rankine cycle. The exact analysis of steam engine is very complex because of the pressure of energy dissipative process such as the friction and heat conduction. So here it is so we'll see the PV diagram of Rankine cycle. So it is the PV diagram of a Rankine cycle. It is defined by a 6 distinct steps A, B, C, D, E, F. The initial case of the working steam is given by the point A. So I can note it here point A. Step 1, it is A to B. This is represented on the indicator diagram by the curve AB. Unit mass of water represented by the point A at a pressure P1 is taken and it is compressed reversibly and adiabatically so as to reach this point P and attain the pressure P2 due to this compression and the adiabatic process. The pressure is P2 attained by that boiler. In this cycle, the temperature may change slightly here, but the volume remains constant. Here, the temperature slightly rises, but the volume is remaining same. Then, second step is point B to C. It is a reversible isobaric heating of a water to its boiling point Tc at its pressure P2. So it is a point B to C. Then third step, it is C to D. It is a reversible isobaric superheating. So here reversible isobaric and it is a isothermal vaporization of water into saturated steam at same temperature Tc and here it is the pressure of that boiling steam is P2 here. The next step it is a step 4 that is D to E. This step is a reversible isobaric superheating of a saturated steam into a superheated steam. It leads here to further increase in a temperature. Then step next one is E to F. It is a reversible adiabatic expansion of a superheated steam to a wet steam at initial pressure P1, and steps next is F to A. This is the last step of the cycle represented by F to A and is reversible isobaric isothermal condensation. This converts the steam back into the water at the initial state A, and the cycle gets completed here at the initial state. Now we will calculate the efficiency of this Rankine cycle. In above step Tc, it is the temperature of the condenser, and Tb is the temperature of a boiler. To calculate the efficiency of a Rankine cycle, we will use the relation, one famous equation, that is H is equal to U plus PV. So here there will be a small changes. If it is happens, then we can write dH is equal to du plus pdv is equal to dq plus vdp, where H is the total heat function, Q is the amount of heat taken, P is the pressure of the system, V is the volume of that system. For if there is a isobaric change, if there is a isobaric change takes place, then dP is equal, change in pressure is 0. Therefore, above equation becomes as dH is equal to dQ. Means what? Here HF minus HI is equal to Q. It is a heat transferred, where HF and HI being the final and initial enthalpy respectively. In the Rankine cycle, the operations B to C, C to D, and D to E are isobaric. So the total heat absorbed per unit mass of working substance during B to E is, here we can write Q1 is equal to HC minus HB plus HD minus HC plus HE minus HD. So total heat absorbed during the working substance is He minus Hb. Here we can write it is equation 1. The operation at F to A, it is a isobaric, this one. So we can, and here heat is rejected. So we can write, let it, we can denote as a Q2. So we can write Q2 is equal to minus of HA minus HF. So it is a HF minus HA. Since the process A to B, here it is the adiabatic compression. Adiabatic compression. We have here, when there is a adiabatic compression is takes place, and there is a heat change in heat energy is 0. That is dq is equal to 0. So we can write here HB minus HA is equal to A to B dH is equal to, if there is a change in 1 to 2 step, we can write phi into dP is equal to, there is a volume is remains the same, but there is a change in pressure. So we can write here P2 minus P1. So therefore we can write here thermal efficiency, thermal efficiency is equal to N Rankine is equal to W upon Q1, means there is a change in work. So we can write here Q1 minus Q2 upon Q1. So we can write here Q1 minus Q2 is, Q1 is what? HE, equation 1 is HE minus HB minus HF minus HA divided by HE minus HP. Okay, so I can take more here page, we can write here. So totally we can arrange this equation as the HE minus HF minus of HB minus HA divided by HE minus HA minus of HB minus HA. From above equations we can write this as a, here HE minus HF minus of P2 minus P1 multiply by phi. So see here, we can substitute HF, HB minus HA this HB minus HA is equal to V into P2 minus P1. Okay. Oh, divided by this HE minus HA minus of P2 minus P1 multiplied by V. So when this actually, when in practice, it is a seen that this HE minus HF is very greater than this P2 minus P1 multiplied by V, and also this HE minus HA is also greater than P2 minus P1 multiplied by V. So therefore we can write N efficiency of a ranking cycle is HE minus HF divided by HE minus HA. The efficiency of this ranking cycle is less than that of an ideal Carnot cycle operating between the same two temperatures. Okay.